Hello, my name is Andrea Caceres, and today I will be talking about my machine learning project about national parks, and I'll talk about my analysis that I went to for crowding and overcrowding in the United States national parks. So for my introduction, I went into a kind of a background about national parks, how they started, who started them. As you can see, back in 1874, the Yosemite Grant was passed by President Abraham Lincoln, saying that the Yosemite Valley and Mariposa Grove will be maintained for the public's use. Then, after that initial bill passed, following presidents created more bills and wanting to protect more areas. And then from there on out, the National Park Service was created. So over the years, interest from the public in these lands has grown exponentially, to say the least. Millions of people from all over the world travel to the United States to enjoy the various activities and attractions that these national parks have to offer. So while national parks were, always a huge hit, they didn't really like blow up in terms of popularity till after COVID. This shift in interest in outdoor recreation and outdoor activities and just being outdoors is called the outdoor boom, which is kind of a loose term to talk about this trend that we see, or it's not even a trend, it's a total change in lifestyle that we've seen in people after the pandemic. I think people saw the outdoors as a way to get out of their houses and still practice social distancing, and it kind of stuck. And after the pandemic hit, people stuck around and wanted to be outdoors more, and therefore the outdoor boom happened. So as visitation continues to increase, understanding these parks, visitation trends, how crowding works, and overall logistics and analysis of these parks is extremely helpful, especially in this administration we have currently in the United States. There are already very limited resources for national parks, and I feel like research like this can really help out the National Park Service in terms of figuring out where to allocate those minimal resources that they have and which parks are doing good, which parks are growing, and which parks, deserve more of that outreach to the public. So yeah, I just kind of went into more of like some practices I'll be using in this project, and talk about how hopefully identifying which variables lead to crowding could be helpful towards the National Park Service in regards of where to put the money, essentially. So yeah, so the 10 questions I will be kind of aiming for during this project in regards to answering are: which national parks are receiving the most visitors? Which national parks experience the largest increase in visitation? What seasonal visitation patterns exist? How did COVID-19 affect national park visitation? Are Pacific Northwest national parks becoming more crowded? What park characteristics are associated with higher crowding? Which parks appear most vulnerable to overcrowding? Can parks be accurately classified by crowding level? How do visitation patterns differ by region? And what role do activities play in visitation and crowding? So for my data preparation and exploratory data analysis, I first want to talk about the data that I pulled. My first data set was the National Park Visitation data. I just pulled this data set from the National Park Service .gov website, and there are a lot of great data sets, and this one seemed very interesting to me because there is each line of code, or each line in this data set, each row is a national park, the unit code, the park type, the region, state, year, month, the total recreation visits for that month and year, non-recreational visits, recreation hours, RV camping, tent camping, backcountry camping, basically all the different types of lodging there is, and that total for each month in the years 2015 to 2025 are recorded in this data set. So I thought that was great to kind of figure out what our visitors doing. So and for cleaning, I dropped column with total values like tent campers total, year total, RV campers total, as they were not necessary. I didn't want the total values for the year. I just wanted the total values for the month in that specific year. The column names were standardized for consistency, commas were removed from numeric strings, and object types were converted to integers. So this is a snapshot of before my data was clean and then after. So for my second data set, I actually requested this data from the National Park Service using an API key. The key is not shown for security purposes, but this data shows basically all the national parks, the state they're in, latitude and longitude, coordinates, park code, activities, and the entrance fee. I thought this data was great because it shows all the different activities, and I decided to create a column that I created a column that showed the total number of activities for each park. And yeah, so here's a snapshot before cleaning and after cleaning, and once again, like I just cleaned up, standardized the column names, and yeah. For my third data set, I combined these two data sets by park code, actually. So each national park has a unique code. For example, Arches National Park, its park code is just Arch. So I was able to use the park code to kind of combine the data sets. And so each row in my combined data set was for a months January through December for 2015 through 2025. So I had a lot of data to work with, which was great. For missing values, there really were none that had to be addressed. There were 20 missing values for entrance fee in the National Parks Service data set. So to address this, I researched the price of the entrance fee for all of those 20 parks that had it missing, and I verified that they were all free to enter. So I guess in the data, they assumed that having no fee entered was free. But of course, I didn't know that, so I decided to input all those manually to show that there is no entrance fee. So here are just links to my data encode for cleaning and for my visualizations, which I'll talk about now. So for EDA, I mainly just wanted to get a lot of background information leading up to my machine learning algorithm. Start off with this layer of understanding of what this data is looking like. I wanted to start with showing the top 10 most visited parks from 2015 to 2025. As you can see from this bar chart, the Great Smoky Mountains really outperforms the rest of the national parks, which was surprising to me as someone who grew up near them. I didn't really know how popular it was, so this was very interesting to see. Then following Great Smoky Mountains, we have the Grand Canyon, Zion, Rocky Mountain, Yellowstone, Yosemite, Acadia, Grand Teton, Olympic, and Glacier National Park. So my next chart is for recreation visits over years 2015 to 2025. I wanted to see kind of how drastic the change was from COVID. And as we can see, this is a pretty drastic change. Uh, yeah, so in 2019 we had around 90 million people visiting national parks, and then it dropped, you know, by a pretty crazy amount. And then 2021, we kind of went back up to around that 90 million threshold. 2022, we had show a little decrease. And then the outdoor boom occurred, which is what I was referencing to earlier, where people wanted to be outside. They didn't want to be cooped up in their houses anymore, so they decided to hit the great outdoors and visit some national parks. And this trend seems to stick. I am sure that 2026 will also show a very similar record-breaking number. Here's another chart showing monthly visitation. I wanted to see which months or season really hits the peak for visitation. And as we can see, summer is the most popular time to visit national parks, which makes sense. Weather is better, school is out, summer vacation is on, and we can see here from this gold star that July was the peak month for visitation for recreation visits. And here I kind of wanted to see whether recreation visits led to more camping. So recreation visit is just like someone like scanning their day pass to go in, or scanning a pass to enter the park, not necessarily a day pass. Does just visiting the park mean there's going to be more camping? And I was kind of hoping to see a much more positive relationship, but it's still positive, but just not as much as I was really expecting there to be between this relationship. And then we have our distribution of recreation visits by region. I decided to use a log scale just for visibility, because not using log scale was very hard to decipher. So as we can see, the kind of lowest recreation visit IQR is for Alaska. This makes sense due to just how, compared to other national parks, Alaska is pretty hard to get to if you're not already in Alaska. And then the region with the highest median was the Northeast region, but it seemed to also have the smallest, or one of the smallest IQRs. And yeah, that's that. And here we have number of activities versus recreation visits. I wanted to see if the park had more activities available, there would be more visits. And this is a very minimally positive relationship. As we can see, I was really expecting more visitors if there's more activities. But I'll reference an example later that kind of talks about why this is. My next chart is for top 10 parks with the most activities. Just not realizing my legend is kind of covering the park with the most activities, but worry not, I can still kind of figure out how many activities there are. So our top park is the Great Sand Dunes National Park in Colorado, with well over 50 activities offered. And yeah, we can kind of see that although, we have this park that offers a lot of activities, it really didn't break the top 10 most visited parks. And Olympic National Park is second runner-up, and that was on the top 10 most visited national parks. But Great Sand Dunes kind of has a couple more activities, so ultimately we can kind of see, like, we're not sure if there is a relationship between activities and visitation, there's a very slightly positive trend. So we know that maybe for some cases, yes, and for some cases, no. For Great Sand Dunes, it was no, it wasn't in the top 10 most visited parks. The next chart is for monthly recreation visits by region. As we can see here, the Intermountain region has the most recreation visits during this 10-year time frame, with over 60 million visitors. So yeah, and the least visited region is Alaska, which makes sense. Once again, it's hard to get there if you're not already there. One thing that did pique my interest was that the Southeast kind of had visitation, peak visitation, not just in the summer, but also in the fall season. We can see that not only is there a peak in July, but there also is one in October. This could be due to leaf peepers, which are people who go to sites like these to see the fall leaves changing colors. So I found that interesting considering, besides maybe the Northeast, that didn't seem to be a very popular trend amongst regions. And here we have a correlation matrix. So we can see this is the correlation matrix between some key variables in the data set. Recreation visits, recreation hours, and all campers all are strongly correlated with each other. This makes sense, as parks that attract more visitors will have more hours recorded and more campers. The most surprising finding here is how weak number of activities is, with the correlations barely reaching 0.2 with other variables. So this kind of supports what we saw earlier. There isn't really a huge relationship between activities and visitation. Also, entrance fees shows weak correlations across all variables, meaning that fee price is not going to be a strong indicator of whether a park is going to have high visitation or not. Here we have the Pacific Northwest visitation trends. So the Pacific Northwest region is made up of Crater Lake National Park, Mount Rainier National Park, North Cascades National Park, and Olympic National Park. Olympic National Park seems to have the most visits compared to the rest. It sees in 2024, it reached over 3.5 million visitors. And yeah, the park with the least visitation, from what we can see here, is North Cascades National Park. So yeah, that is my data preparation and EDA. And my next section will be on clustering. So for clustering, clustering is an unsupervised exploratory data analysis technique used to identify groupings of similar data points and putting them into clusters. Unlike supervised learning, clustering does not have a target variable or labels. These groups are based on similarities in the data, grouping them together while differing from other groups. So there are two methods of clustering. We have partitional and hierarchical clustering. Partitional clustering, such as k-means, requires a predefined number of clusters prior to running the algorithm. Hierarchical clustering does not need a certain amount of clusters prior to running, because it groups data based on similarity. So similarity is based on distance metrics. So we have Euclidean distance is calculated by measuring the straight line distance between 2 points in a space, and non-Euclidean distance, such as cosine similarity, measures the cosine angle between points in a multi-dimensional space. So for my project, clustering will help identify which national parks are similar in terms of visitation trends and park characteristics. So here we have a small example that shows unlabeled data and cluster data, kind of a before and after. So before, there are no groups. We don't know what data points are similar with each other. We don't know what certain groups mean. And then on the right, we have the after, which is cluster data. We have 3 groups here, and within each group, those data points are similar enough to one another to differentiate from the other groups. So a dendrogram is just a visual of hierarchical clustering. As you can see here, this dendrogram has grouped A, B, and so forth. So for data preparation, clustering requires numeric and unlabeled data because, like we said, it measures similarity between observations with distance calculations. Categorical variables such as park name, park code, and state were removed from the analysis, and only numeric variables related to park characteristics were used to form clusters. So the dataset was aggregated by park name with the mean value calculated for each selected feature, resulting in 1 row per national park. Visitation data was removed after initial k-means results showed clusters were driven primarily by differences in visitation volume, obscuring other meaningful groupings. So basically that means I didn't want these clusters to be formed just solely based on volume of visits and hours. I wanted to see what other characteristics could influence grouping. So, yeah. Before scaling, the selected variables had very different numerical ranges. I used standard scalar to transform each variable so then it had a mean near 0 and a standard deviation near 1. So this helps prevent variables with larger values from having too much influence on distance calculations used by k-means. So here we have just a screenshot of my data before scaling. The variables had various different numerical ranges, and here we have an after screenshot after kind of standardizing. And here we have links to my data set and to my code. So to determine the optimal number of clusters, I used a elbow plot and silhouette scores. An elbow plot kind of just tells you like which number of clusters is optimal, and the most bend that there is in the elbow kind of tells you which number that is. So as we can see here, this one was really kind of difficult for me to decipher. I believed it was between maybe 3 or 5. I couldn't really tell, which is why silhouette scores come in handy. So the elbow plot kind of told us that the optimal number of clusters was around 4 or 5, because that's where the curve really begins to bend. However, the silhouette scores told us kind of a different story. 2 clusters produced the highest silhouette score of 0.605, indicating that 2 clusters had the clearest separation between groups. But although, 2 clusters produced the highest silhouette score, it only divided the parks into 2 really broad groups. So like I was saying, 2 clusters really just divided the parks into 2 super broad groups and didn't really provide a lot of detail about what is causing that differentiation. So I thought that 3 clusters and 4 clusters created more meaningful groupings. So I kind of separated the parks by not really visited parks, popular recreation-based parks, then we have our major destination parks, and then we have our craziest park, the Great Smoky Mountains National Park, which is, I'll get into that. So after all this analyzing, like 2 clusters seem to be the strongest solution, but I feel like 4 clusters was more useful in regards to what is really causing these parks to stand apart from one another. So ultimately, I decided to stick with 4 clusters. So as we can see here, 2 clusters, 2 clusters just was like, okay, here are all these parks that, are least visited, and then here's the parks that always come to mind when you think of national parks. And I thought that was kind of, a cheap out. I wanted more differentiation, I wanted to kind of see what could be forced into groups. So here are just more metrics about cluster 0 and cluster 1 that you are more than welcome to look at on my website. And then for 3 clusters, here we're kind of seeing a little more, but not really, because we have cluster 0, which is just the majority of parks. And then we have those really big name major destination parks. And then the only national park in our 3rd cluster was the Great Smoky Mountains. And this was interesting because, like, it only contained the Great Smoky Mountains. And this was solely based on, or not solely based, but here I'll kind of talk about it. The average number of non-recreation visits for the Great Smoky Mountains was 893,553 visits, and concessionaire lodging averages around 880. Concessionaire camping has a mean of 0, and there are around 15,000 tent campers and 11,000 RV campers on average. Backcountry campers averaged around 7,000, which is less than Cluster 1, which is our major destination parks. And miscellaneous overnight stays were around 2,000. And finally, I think what causes the Great Smoky Mountains to really stand apart is that $0 entrance fee. The big name ones, Grand Teton, Yosemite, Yellowstone, Olympic, Grand Canyon, those all had an entrance fee average of, $33. Comparing that to just, free entrance, that is huge. So for 4 clusters, we have, the majority of the parks are in cluster 0. Then for cluster 1, we have some, big name brand national parks. Our 2nd cluster is Great Smoky Mountains. Then our 3rd cluster is kind of just a spread of some big name and then some not very well known national parks. So yeah, let's dive into this. So 4 clusters revealed 4 distinct groups. The largest difference between clusters were in lodging, camping, backcountry use, entrance fee, suggesting that recreation infrastructure and overnight opportunities were the main drivers of this cluster formation. So now we have our hierarchical clustering in our dendrogram. So our hierarchical clustering dendrogram showing us how parks are grouped based on cosine similarity. Parks that are merging at a lower distance are more similar, and parks that merge at a higher distance are less similar. So as you can see, Yellowstone, which is somewhere here, and Yosemite joined at a very low distance, indicating that they share many recreation and visitor characteristics. The Grand Canyon also joined this group early, suggesting similar patterns of camping, lodging, and recreation activity. The Great Smoky Mountains remain separate from most parks until a much higher distance, reflecting how unique it is, and which is consistent with our results that we saw with K-means, since it's formed its own cluster in both 3 and 4 clusters. The major branch separations in the dendrogram suggest that 3 to 4 clusters is appropriate, which aligns with what we saw in K-means. So ultimately, clustering successfully identified meaningful groups in national parks based on park profiles and their characteristics. 2 clusters separated standard parks from major destinations, while 3 and 4 revealed additional structure within our data. The Great Smoky Mountains consistently formed its own cluster due to how many people visit, how there's no entrance fee, how there's other unique properties. And although the 2 cluster solution had the highest silhouette score, the 4 cluster solution was selected because it provided more distinction amongst national parks. And hierarchical clustering supported this interpretation by showing similar major groupings. So our next algorithm is our principal component analysis. Principal component analysis, or PCA, is a statistical process that conducts dimensionality reduction. Basically, we reduce the number of features in a data set while still keeping most of the information. So PCA uses eigenvectors to define what the directions are of the axes. The axes are the principal components. Eigenvalues represent the amount of variance explained along each of those directions, and components with higher eigenvalues capture more information and therefore minimize loss. Dimensionality reduction is the process of removing features while minimizing information loss and explaining the most of the variance. PCA is really important because having fewer features helps with computational efficiency, reduces noise, and makes data easier to analyze. So here we have an example of what PCA can look like. As we can see here, we have different directions, and the directions are the eigenvectors, and the eigenvalues are the amount of variance explained along each of those directions. So for data preparation, we are still going to use that aggregated park data that we used for clustering. So yeah, here's the link to that data set and the link to the Python code used for PCA that I did. So here's just a brief little rundown of dimensionality reduction. It's a technique used in machine learning and data analysis, reduces the number of variables in the data set while retaining the critical information. That ultimately helps simplify complex data sets. So PCA worked well with my project. So it did ultimately reduce the dimensionality. So PCA was performed on standardized park level features. The first principal component explained 36.9% of the variance in the data, while the second explained 19.7%. Together, that accounts for 56.6% of the total variance, indicating that the majority of the information contained in those original 10 variables could be summarized by only using 2 dimensions. So since most of the national parks seem to gather together, we could say that they have similar recreation, camping, lodging, visitation characteristics. But we do have some notable outliers. So Saguaro National Park seems to be the most separated over here from the left group of parks. So this left group, it seems to be separated along that Y, or along the first or the second principal component. So from this table, we can see that non-recreation visits and non-recreation hours contribute most to the second principal component, which may help explain why Saguaro is separated from other parks. Yosemite is high on principal component 1, as we can see here, meaning that its camping, lodging, and backcountry recreation characteristics are more unique compared to the other parks. And then we have our good park, our crazy park, the Great Smoky Mountains. It's the most obvious outlier because of how unique of a profile it is compared to other parks. So here we have the scree plot. So the bend in the scree plot is around the 4th principal component, suggesting that the first 4 principal components capture most of the variance, and after that 4th principal component, the amount of variance explained starts to decrease, indicating that we don't need more than 4, and these additional components are contributing less new information. So this suggests that the variation in national parks can be captured using a few principal components rather than all 10. So we can see that principal component 1 was influenced by basically overall overnight recreation activity, tent campers, RV campers, concessionaire lodging, and backcountry recreation. The second principal component was driven by non-recreation visits and non-recreation hours, indicating that it captures differences in non-recreational park usage. So for conclusions, through PCA, the number of features was reduced from 10 variables into a smaller number of principal components. and all this while still minimizing information loss. The first two principal components explain 56.6% of the total variance and revealed that camping, lodging, backcountry, and non-recreation visitation were the primary factors causing differences among national parks. These PCA results go hand in hand with clustering by finding that major destination national parks such as Yosemite, Yellowstone, Grand Canyon, and the Great Smoky Mountains are much different from the other majority of parks. Overall, PCA was very useful and help simplify the data and better understand what key characteristics are associated with national park visitation and recreational patterns. Hello, so my next section is naive Bayes. Naive Bayes is a supervised classification algorithm that uses Bayes' theorem with an assumption of naivety to split up data observation into predefined categories. So using Bayes' theorem, the model calculates the probability that an observation should go in each category based on its properties. The reason why Bayes is naive is because it assumes that all the features are independent of each other within each class. Multinomial Bayes is used for non-negative numeric frequency or account data. Bernoulli naive Bayes is for binary variables, so each data observation would either be 0 or 1. For my project, I will use multinomial naive Bayes to classify national parks into low, medium, and high visitation levels. The feature types used to classify the national parks are camping, recreation, activities, entrance fees, and region characteristics. So here is my sample data. I am using the same aggregated park data. To create labeled data for supervised learning, the parks were classified into low, medium, and high visitation categories using recreation visits. Because these labels were derived from the visitation data, recreation visits and recreation hours were excluded from the predictor variables to prevent data leakage. The model used recreation, lodging, camping, and overnight stay, and entrance fee characteristics to predict visitation level. So the data was split into a training and a testing set using an 80-20 split. First, the features were split from their labels, and crowding levels was created by grouping recreation visits into low, medium, and high categories. I used stratification, so each class is represented in both data sets. The model was trained on the training set and then evaluated using the testing set. This was done to verify that the results reflect how good the model performs on new and unseen data. So here we have the training data after the split, the test data after the split, and our results resulted in an accuracy score of 58.3%. And here is our confusion matrix. So for just some more results, the supervised classification system could classify parks into different levels of visitation: low visitation, medium, and high, better than random guessing. Random guessing would have an accuracy of around 33%, and our accuracy score was 58.3. So we can say that naive Bayes did better than random guessing. The first row shows that 2 low visitation parks were correctly predicted as low. 1 low visitation park was incorrectly predicted as medium, and 1 low visitation park was incorrectly predicted as high. The second row shows that 3 medium visitation parks were correctly classified as medium, 1 medium visitation park was wrongly classified as high, and none were classified as low. The last row shows that 2 high visitation parks were correctly identified, 1 was wrongly classified as low, and 1 was wrongly classified as medium visitation. So from this naive Bayes analysis, it showed that national park visitation levels can be partially predicted by using park activity and certain features such as camping, lodging, recreational activity, and etc. The model was able to differentiate low, medium, and high visitation levels better than random guessing. So this suggests that there are meaningful patterns in how different types of parks utilization relates to overall crowding. However, the 58.3% accuracy also shows that these patterns are not perfectly separable, and there is still overlap between visitation levels that the model does not entirely capture. So the next classifier we decided to use was decision trees. Decision trees is a supervised machine learning algorithm used for classification and regression tests that break down data sets into predefined categories or numerical targets using a series of tree-like rules. To determine the most effective feature to split the data at each node, the algorithm calculates and compares data using metrics known as entropy or Gini, and ultimately selects the split that yields the highest information gain by reducing overall noise. So here we have an example of what a decision tree can look like. As you can see, these are the nodes, these are the branches, and down here are the children. So yeah. Entropy and Gini indexes are used to measure how mixed up a group of data is at any given point. Entropy uses logarithmic scales to find peer groups, and Gini calculates the probability of misclassification and can ultimately be faster than entropy. The algorithm then calculates information gain, which measures the actual drop and mix-up after a split, and it always will make the best choice by selecting the split that most clears up confusion. So here are those criteria. There's Gini and entropy. Here is the sample data for decision trees. We used that aggregated park data to see if we could classify data into low, medium, and high visitation categories using recreation visits. So we trained our data and then we tested it on unseen new data. And well, these are our results. Here is our entropy decision tree. Here is the little image for that. So the decision tree with the entropy criteria is used to measure node impurity. This criterion calculates mathematical randomness of the data on a logarithmic scale. It runs without any depth limits or restrictions for splitting, and it continues each branch until every node achieves an entropy score of 0. So here we have the Gini decision tree. The second tree that we just saw uses Gini, and it measures the probability of a data point being misclassified based on the distribution in that node. It also runs without structural limits, and it splits entirely by decreasing misclassification. And here we have a custom entropy decision tree. So our third tree uses the entropy criteria but has a custom hyperparameter set at a minimum impurity decrease threshold of 0.06. So the model will test possible splits and completely stops growth of a branch if the next split fails to improve the total tree impurity by at least 6%. So here we have the accuracy scores for each of the trees. And as we can see, our custom entropy test performed the best. And it had an accuracy score of 50%. So here's our confusion matrix plot. So as we can see, the supervised classification system could classify national parks into low, medium, and high visitation better than random guessing. And the report above, the accuracy level is 50%. Since random guessing would have had an accuracy rate of 33%, the model performed better than chance, but it did perform worse than naive Bayes, which had a score of 58.3% accuracy. So as you can see here, our first row shows that 3 low visitation parks were correctly predicted as low, none were incorrectly predicted as medium, and 1 was incorrectly predicted as high. Our second row shows that none of the medium visitation parks were correctly classified as medium. 2 were misclassified as low, and 2 were misclassified as high. And our last row shows that 3 visitation parks that were high were correctly identified as high, one was misclassified as low, and none were misclassified as medium. The decision tree analysis demonstrated that national park crowding levels can be partially predicted by looking at the characteristics that each park has. The test accuracy of 50% shows that the algorithm did do better than random chance, and it revealed the relationship between park use assets and visitor traffic. However, the breakdown of the prediction states that these patterns are heavily overlapped, and it is seen in the middle range of visitation. The algorithm failed to identify any medium visitation parks and split them evenly between low and high instead. It's clear that these features cannot be the only ones needed to forecast park crowding levels when using decision trees. Future models could benefit from incorporating more features. Support vector machine is a supervised learning algorithm that finds the best hyperplane that cuts through classes in classification. So the goal of a support vector machine is to maximize the margin for better classification performance. SVM requires numeric data because every data point is treated as a geometric vector in a multi-dimensional space, and it attempts to draw a physical boundary through that space. Linear separators are the decision boundary between one class and another in feature space. The kernel is a function that projects data onto a higher dimensional space for nonlinear data to find separation. The dot product is critical to use because it measures the relationship between two data points to see how similar they are. The polynomial kernel allows the support vector machine to learn nonlinear boundaries by mapping the data into a higher dimensional feature space without having to calculate new coordinates. The RBF kernel measures similarity between points by applying a Gaussian function to the squared Euclidean distance, so that points closer together receive a higher kernel value rather than those not as close together, and points farther apart will approach zero. So here we can see how we will have an input space, and then it will convert into a feature space. And you can see that hyperplane is cutting the blue dots from the red dots and having a physical boundary between those two classifications. And here we have the different kernel types. And here I have done a demonstration on how a 2D point can be mapped onto a higher dimensional space. So for data prep, we used our aggregated park data. SVM requires label observations in a binary target variable. High crowding was created. Once again, I decided to split the training set into 75%, and the testing set would be 25% of the data. And yeah, the training set was used to build the SVM model and test it on unseen data. Another thing is the observations above the median amount of recreation visits were labeled 1, and those below were labeled 0. So SVM, we are using a binary response. And the goal of creating this binary target was to train the SVM classifier to predict whether a national park is likely to experience high or low crowding based on its characteristics. So our results, to test each kernel, we did 3 different cost values were used, 0.1, 1, 10. Cost values determine how strict penalties will be for misclassifications. So our first one we have here is for our linear kernel. And from the confusion matrix, we can see that our linear kernel did not perform well. 6 out of 15 parks were classified correctly, and 9 were classified incorrectly. 5 low crowding parks were identified as high, and 4 high crowding parks were classified as low. From this, we can see that the relationship between predictor variables and crowding level is not, easily separated with just a linear boundary. We're going to have to use something, non-linear. So our next kernel type is polynomial, And from our confusion matrix, we can see that the polynomial kernel performed better than the linear. 9 out of 15 parts were classified correctly, and 6 parts were misclassified. The model identified 7 low crowding parts correctly and 2 high crowding parts. However, the model classified 5 high crowding parts as low crowding, showing that it still struggled to identify parts with high crowding. The polynomial kernel had the highest accuracy, but it was better at identifying low crowded parts compared to high crowded parts. And then we have our RBF kernel, or our Gaussian kernel. And from our confusion matrix, we can see that the RBF kernel performs slightly better than our linear kernel, but still not as good as our polynomial. 7 out of 15 parts were classified correctly, and 8 parts were misclassified. 3 low crowding parks were correctly identified, and 4 high crowding parks were classified correctly. 5 low crowding parks were classified as high, and 3 high crowding parks were classified as low. So the RBF kernel was in second place, and it was more balanced in identifying both classes, but its overall accuracy was still lower than the polynomial. So here we can see those comparisons of accuracy scores amongst the 3. So to conclude, our support vector machine model helped in this research because it provided further analysis as to what features lead to high crowding in national parks. Through PCA and clustering, we learned that crowding is more complex than simply relying on visitor count. The polynomial kernel, being the method with best accuracy, showed that recreational lodging activities, non-recreation activity features do not have a linear relationship with crowding, but rather something more complex. And these results matter because they can show the National Park Service that data mining methods can be used to identify parks that need more resources, staffing, transportation, planning, or even visitor management. Okay, our last tab is about neural networks. Neural networks are a machine learning model that is similar in function to the human brain. They're made up of nodes that are interconnected and process and learn patterns in data in order to recognize patterns. These nodes are similar to neurons in our brain, in which they receive inputs and each works with thresholds in an activation function. The links between them carry information and are regulated with weights and biases, which determine the strength and influences of these links. There are propagation functions, which are mechanisms that process data across the layers of nodes. Neural networks have a learning rule, which allows the method to adjust weights and biases over time to improve accuracy. Neural networks work in 3 stages. The first is that data is fed to the network, which is the input. Then the network generates output based on current parameters. And finally, there is an iterative refinement where weights and biases are adjusted to improve performance of the network. So here we have an image. We have our input layer, our hidden layer, and our output layer. These are nodes, and we have our links between them, which have their own weights and biases. And yeah, so here is our sample data. And once again, I use the aggregated park data. Neural networks use numeric predictor variables and a known target variable. So I, once again, used a binary target variable named high crowding. Parks above the median number of visits were labeled 1, and below that were 0 for low crowding. Training data, test data, and here are our results. So here we have our last 5 neural network training epochs. The final 5 epochs show that training loss continued to decrease from 0.29 at epoch 496 to 0.290374 at epoch 500. This means that the neural network was still making small improvements as it adjusted the weights. These changes were very small, suggesting that the model is beginning to converge and that additional epochs were likely to only produce small improvements. So here we have our neural network training loss plot. It decreased throughout the 500 training epochs, dropping from approximately 0.85 to 0.29. This indicates that the neural network successfully learned patterns in the training data and reduced prediction error as the weights were updated through backpropagation. The curve decreases during earlier epochs before leveling off around the end of training. This means that the model was beginning to converge. Since the loss continued to decrease without sudden increase, the training process was effective. And here we have our confusion matrix. From the confusion matrix, the neural network classified 7 out of 15 parts correctly. And this resulted in overall accuracy of only 46.7%, which is below the 50% accuracy that would be expected from random guessing. This shows that the neural network was unable to find a reliable predictive relationship between part characteristics and crowding level, unfortunately. And in conclusion, the neural network was another way to predict whether there would be high or low crowding in a national park. As we can see, 7 out of 15 parts were classified correctly. The errors were distributed evenly between low and high crowding classes rather than favoring one. This performance is slightly below what would be expected from random guessing, as said. But yeah, so compared to other supervised learning methods, this one did not perform as good as our support vector machine did, and specifically our polynomial kernel. Yeah, so a likely explanation to that is that the small number of national parks available provided limited data for a model with various weights. So this made it difficult for the network to generalize. Maybe a larger data set or more part characteristics could provide stronger performance. But overall, the results support the project's conclusion that national park crowding is influenced by multiple factors that interact with one another. And model choice is super important, and data amount is also super important when applying these machine learning algorithms. And yeah. Hi guys, just to keep this short and sweet, I figured I'd go over the conclusions just a little bit. So our top 10 visited national parks were Great Smoky Mountains, Grand Canyon, Zion, Rocky Mountain, Yellowstone, Yosemite, Acadia, Grand Teton, Olympic, and Glacier. We saw that July was a peak month for visitation. We saw that although we did have one park with the most amount of activities, it didn't result in being in the top 10 most visited national parks. We saw that the Intermountain region had the most visitation, and we saw that clustering in PCA gave us a clear picture on how national parks grew together based on its characteristics. We saw that 4 clusters really uncovered a really good distinction between this data and groups of national parks and ultimately what's going on underneath. PCA, we were able to reduce 10 original variables down to a smaller set of just 2 principal components that explained around 56.6% of the total variance. We did 4 supervised models, naive Bayes and decision tree, predicted 3 visitation levels. Ultimately, naive Bayes reached an accuracy score of 58.3, which beat that, 33% chance for just random guessing. And then support vector machines and neural networks were used to predict binary crowding label. We saw that our polynomial support vector machine worked best, and our neural network did worse than random guessing. And yeah, these findings have really used for the National Park Service. And I won't go on much longer, but the biggest takeaway is that no single park characteristic is going to drive the answer to all these questions. Ultimately, it's all factors intertwining. But yeah, that is my conclusion. And I know this research and more time into this would be really great. I really appreciate you guys for taking the time out of your day to watch this video. And yeah, I hope you have learned a bunch. And I know I have. This class has been great. This semester has been great. I've learned a bunch. And yeah, this was just overall such a fun project. So thank you guys. And please review the website. Please go over the conclusions. And yeah, I just want to say, ultimately, we found a lot of algorithms that work with classifying crowding. This type of work could be great for the National Park Service to use to figure out where their very limited resources could go to. And ultimately, I know with more data and more time and maybe even some time series analysis, this project could evolve into something greater and grander and have really great prediction power. And yeah, for the scope of this class, I am happy with my results. And thank you so much.